Hi and Assalamualaikum. Today in this video, we are going to explain more in detail about crystal defects. Before we explain about the crystal defect in detail, let me first introduce my group members. First, we have Nur Ain Shahinda, Ahmad Syami, Saiful Alif, and myself, Wen Siti Amirah.
Hi, my name is Nur Ain Binti Azam, and today we're going to explain to you what are the crystal defects. But first, I'm going to tell you what are the objectives of this video. By the end of this video, we should be able to define crystal defects, identify and classify the main type of crystal defects. Last but not least, explain each type of crystal defects by describing its formation, characteristic, and their common example. So, next, moving on to the introduction. Now, I'm going to tell you what is a crystal defect. Crystal defect is a certain irregularity of imperfection in the arrangement of crystal structure. It is manifested in the phenomenon that the arrangement of particles deviates from the periodic repetition of the spatial lattice law in the local area of the crystal structure and appears disordered. These imperfections result from deformation of the solids, rapid cooling from high temperature, or high energy radiation, such as X-ray or neutron, striking in the solid, located at a single point, along lines, or on whole surface in the solids. These defects influence its mechanical, electrical, and optical behavior. So, moving on to the types of crystal defects. So, crystal defects have two types. First is stoichiometric defects, and two is non-stoichiometric defects. So, first, for stoichiometric defects, there are four types of defects, which are vacancy, Scotchy, interstitial, and Frankel. So, next, for non-stoichiometric defects, there are two types of it, which is metal axis and metal deficiency. Crystal defects are intentional in the material science because they can affect the material strength, ductility, and the deformation behavior, which are critical for various applications.
Right, so the first stoichiometric defect that I'm going to touch is the vacancy defect. This occurs when an atom is missing from its regular atomic site, leaving the later site weakened. This defect usually develops when a substance is heated. So at high temperature, atoms vibrate around their position, and some require enough energy to leave the site completely. Because atoms are missing, the density of the substance will decrease. The second type is interstitial defect. This happens when an atom occupies a position in the lattice that it's not normally occupied in a perfect crystal. Because of this, the total number of atoms become larger than the number of regular lattice sites. As a result, the addition of these extra atoms causes an increase in the density of the substance. Now, we move to defects specific to ionic crystal, starting with the Schottky defect. This is a defect where a pair of consisting one of cation and one anion is missing from their regular sites. To maintain electrical neutrality, the number of missing cation must always equal the number of missing anion. This defect is common in compound where the cation and anion are almost similar in size, such as sodium chloride and potassium chloride. Because ions leave the crystal, so the density of the solid may decrease. The final type is the Frankel defect. In this case, an ion, usually the smaller cation, is displaced from its regular site into an interstitial void or void space. So an ion are generally too large to be displaced this way. This defect is common when an ion is much more larger than the cation, such as in silver chloride and zinc sulfide. Importantly, since no atoms actually leave the solid, the density will remain the same and the overall electrical neutrality is maintained. To conclude my part, let's summarize the key difference between the most common ionic defect, which is Frankel and Schottky defect. In Schottky defect, both cations and anions leave the crystal, whereas in Frankel defect, the smaller ions simply shift to an interstitial position. Next, one Schottky defect reduces the count by 2 atoms, while the atom count in Frankel defect remain the same. And the most importantly for our analysis, Schottky defect reduce the density of the solid, while Frankel defects have no effect on the density.
For non-stoichiometric defect, they are divided into two. First one is metal excess, and the second one is metal deficiency. For metal excess, they are occur in two different ways. And the first one is F center or color center, and the second way is adhesion ion and electron. For the F center, in this defect, an ion is missing from its normal lattice side, and the resulting vacancy is occupied by an electron. Such defects are known as F-center. The trapped electron is occupied in the musical region and is mainly responsible for the color of the crystal. This type of defect is commonly found in Schottky defect by forming compound. For example, a colorless stoichiometric sodium chloride crystal, when heated in the presence of sodium or potassium vapor, it will rapidly quench and incorporate extra sodium or potassium atom into the lattice. This atom ionizes to form sodium or potassium ion that occupy normal cation site, while the electron become trapped in anion vacancies, forming F-center. As a result, the sodium chloride crystal turn into yellow color. For the interstitial ion and electron, this defect occurs when the cation moves into an interstitial site, and an electron is also present in an interstitial position to maintain electrical neutrality. This type of defect is commonly found in crystal exhibiting Frankel defect and is generally observed in compounds such as zinc oxide, iron oxide, and cadmium oxide. For metal deficiency defects, there are also two ways that decay occurs. The first one is when the positive ion is absent, and the second one is extra interstitial negative ion. For the positive ion absence, this defect occurs when one or more cations are missing from their normal lattice site, creating cation vacancies. To maintain charge balance, the nearby cation will gain additional positive charge and are converted into cation with higher oxidation state. And this type of defect is found in ionic crystal, in which the metal ion exhibit variable oxidation state, such as iron oxide, nitro oxide, and iron sulfur. This crystal containing metal deposition defect behave as semiconductor. Electrical conductivity arises from the movement of electron between cations. So when an electron moves away from a cation, that cation attains a higher positive oxidation state. And this process is described as the movement of positive holes, and such material are classified as p-type semiconductor. For extra interstitial negative ion, this defect occurs when an extra negative ion occupies an interstitial position. To maintain charge balance, a nearby cation acquires an additional positive charge. However, since negative ions are generally large, it is difficult for them to fit into interstitial site. As a result, no crystal containing such as negative interstitial ion is known as crystal. For the differences between stoichiometric defect and non-stoichiometric defect. For stoichiometric defect, there are imperfections in the crystallities that do not change the chemical composition of a compound. Although atoms or ion may be missing or displaced within the structure, the ratio of cation to an ion remains the same. So the compound still follow its original stoichiometry. For example of stoichiometric defect includes structure defect, where equal number of positive and negative ion are missing, and Frankel defect, where an ion moves from its normal lattice position to an implicit site. In all these cases, the overall chemical formula of the compound remains unchanged. In contrast, non-stoichiometric defects are crystal defects that will alter the stoichiometry of a compound by changing the ratio of metal ion to non-metal ion. These defects are common in transition metal compounds and result in composition that do not have exact whole number ratio. Non-stoichiometric defects include metal excess defect, where extra metal ion or electron are present, and metal deficiency defect, where some metal ions are missing and neighboring ions change their oxidation state to maintain the charge balance. And as a result, both the crystal structure and the chemical composition of the compound are affected.
In conclusion, although crystalline solids have a very regular structure, in reality no crystal is perfect. Most crystals contain defects which are small irregularities in the arrangement of particles, known as crystal defects. We learned that defects like vacancy, Schottky, and Frankel defects happen when atoms or ions are missing or displaced from their normal positions, while non-stoichiometric defects occur when the ratio of particles is not ideal. These defects are important because they affect real properties such as density, conductivity, and even the color of crystals. For example, in ionic solid with color centers. Therefore, crystal defects are not just imperfections, but they help us understand the real behavior and practical application of crystalline materials. That's all from us. Thank you.